Hi, my name is Damien Neil. I work on the Go team, and I'm here to talk about testing asynchronous or concurrent code in general and code that uses time in particular. And to start with, let's establish some terminology. A synchronous function is pretty simple. You call it, it does something, and it returns. An asynchronous function is different. You call it, it returns, and then it does something. As a concrete, if somewhat constructed example, cleanup up here is a synchronous function. You call it, it deletes some cache directory, and it returns. But cleanup in background is an asynchronous function. You call it, it returns, and the cache directory is deleted sooner or later. Sometimes an asynchronous function does something at some point in the future. For example, the context package includes a withDeadline function that returns a context that will be canceled in the future. And when I talk about testing concurrent code, I mean testing these sorts of asynchronous operations, both the ones that use time and the ones that do not. A test verifies that a system behaves the way we expect it to. There's a lot of terminology around unit tests, integration tests, and so on. But for our purposes today, every kind of test reduces to 3 steps. Set up some initial conditions, tell the system under test to do something, and then verify the result. Testing a synchronous function is quite straightforward. You set up your initial conditions, you call your function, it does something, it returns, and you verify the result. But testing an asynchronous function can be quite tricky. You call the function, it returns, you then wait for it to finish doing whatever it does, and then you verify the result. If you don't wait the correct amount of time, you might find yourself verifying the result of an operation that hasn't happened yet, or one which is still in the process of happening, and this never ends well. Testing an asynchronous function is especially tricky when you want to assert that something has not happened. You can verify that the thing has not happened yet, but how do you know with certainty that it's not going to happen later? To make things a little more concrete, let's work with a real-world example. So let's consider the context package's withDeadline function again. There are 2 very obvious tests to write for this function. First, before the deadline, the context is not canceled. And second, after the deadline, the context is canceled. So let's write a test. To keep the amount of code on these slides marginally less overwhelming, we'll just test the second of these cases. After the deadline expires, the context is canceled. This looks like a great test, right? Raise your hand if you see a problem. A couple of you are paying attention. So this test obviously does have a problem. We're sleeping until the exact moment when the deadline expires. Odds are very good that the context has not been canceled yet by the time we examine it. The test is racing with the operation that we're examining. At the very best, this test is going to be very flaky. So let's fix it. We'll just sleep until 100 milliseconds after the deadline. 100 milliseconds is an absolute eternity in computer terms. You can do so many things in 100 milliseconds. This should be fine. Unfortunately, we still do have 2 problems. First, this test takes 1.1 seconds to execute. That's really slow. This is a simple test. It should take a millisecond at the very most. Even a millisecond seems pretty slow. And second, this test is still flaky. 100 milliseconds is indeed an eternity in computer terms, although we're very good at filling it up with other nonsense. But on an overloaded CI system, it's really not unusual to see pause times lasting much longer than this. I would expect this test to pass pretty consistently on a developer's workstation or laptop, but I would also expect it to be occasionally flaky on a CI system. So tests which use real time are always slow, flaky, or usually both. If you wait longer than necessary, your test is slow. If you don't wait long enough, your test is flaky. You can make the test more slow and less flaky, or you can make it more flaky and less slow. Did I just say the same thing twice? I might have. But you can't make it fast and reliable. We have a lot of tests in the net/HTTP package which use real time, and they're basically all slow and or flaky, which is what started me down the road, which leads me to standing here today under these extremely bright lights. So, what do we do if we don't sleep? The simplest way to test an asynchronous function is to not do it. The simplest way to test an asynchronous function is to not do it. Synchronous functions are easy to test. If you can transform your asynchronous function into a synchronous one, it will be easier to test. For example, if we consider our cache cleanup functions from a little bit earlier, the synchronous function is obviously better. It's easier to test, and the caller can easily start a new Go routine to run it in the background if you did want it to run concurrently. As a general rule, the higher up the call stack you can push your concurrency, the better. Unfortunately, this sort of transformation isn't always possible. With Deadline, for example, is an inherently asynchronous API. A better approach is to make our code more testable. And here's an example of what this might look like for our with Deadline test. Oops. So instead of using real time, we'll use a fake time implementation. Using fake time avoids unnecessarily slow tests because we never wait around doing nothing. It also helps avoid test flakiness, since the current time only changes when the test adjusts it. There are various fake time packages out there, or you can write your own. It's not particularly difficult. We need to modify our API, however, to accept a fake clock. So here I've added a with deadline clock function that takes an additional parameter. And when we advance our fake clock, we have a problem. Advancing the current time is an asynchronous operation. When you advance time, many things happen. Sleeping Go routines will wake up. Time.timers will send on their channels, and something might be reading from that channel. Time.tickers also send on channels. Time.afterfunc functions run in new Go routines. All of these things are asynchronous behaviors. So we need to wait for all that work to finish before we can test the expected behavior of our system. We don't know how with deadline is implemented here. We don't know which one of these methods it's using to wait for this deadline. But simply advancing the clock doesn't tell us that it's finished its work. So I've added a wait until idle function here, which waits until any background work related to some context has completed. And this is a very simple example, very trivial, but it does demonstrate the two fundamental principles of writing testable concurrent code. First, if you use time, use fake time in your tests. And second, have some way of waiting for quiescence, which is a very fancy way of saying that all background activity has stopped and the system is stable so we can examine it. The interesting question, of course, is how do we do this? I've glossed over all the details in this example because there are some pretty big downsides to the approach of simply instrumenting your code. First off, it's hard. Using a fake clock isn't difficult, but identifying when background concurrent work is finished and it's safe to examine the state of the system really is. Your code becomes less idiomatic. You can't use standard time package functions. You have to use whatever your fake clock uses. You can't just start a Go routine without somehow tracking the lifetime of that Go routine and when it quiesces. You also need to instrument not just your code, but any package of other third-party code that you might call. So if you do use third-party code that has any concurrent behaviors, you're probably just out of luck. It doesn't use the same fake clock that you do. It might not, probably doesn't, provide a way of waiting for quiescence. But really, from my perspective, the worst problem with this approach is that it can be just about impossible to retrofit into an existing code base. I attempted to apply the approach of more instrumentation to Go's HTTP implementation, with the goal of making our tests fast and reliable. And I did have some success in doing so in some places. But the HTTP2 server defeated me. I could not figure out how to add instrumentation to detect quiescence without essentially rewriting it. It just seemed infeasible, or at least beyond my skills. So what do we do if we can't make our code testable? Well, what if instead of instrumenting our code, we had a way to observe the behavior of the uninstrumented system? A Go program consists of a set of Go routines. These Go routines have states. We just need to wait until all the Go routines have stopped running. Unfortunately, the Go runtime doesn't provide any way to tell what these Go routines are doing. Or does it? The runtime package does contain this function called stack that gives us a stack trace for every running Go routine, as well as the states of every running Go routine. It gives it to us as readable text intended for human consumption and debugging, but we could parse that output. Could we use this to detect quiescence? Now, this is obviously a terrible idea. There is no guarantee that the format of these stacks stays stable over time. There's no guarantee that this set of Go routine states stays stable over time. This will break. You should not do this. So I did it. And it worked. It worked surprisingly well, somewhat terrifyingly so. With a fake clock, a little bit of instrumentation to tell what Go routines are part of a test, and some horrifying abuse of runtime.stack, I finally had a way of writing fast, reliable tests for the HTTP package. And in fact, we today still have some tests of the HTTP2 server which use this approach. The underlying implementation was absolutely horrible. But this did demonstrate that there was a useful concept here. Go may have built-in concurrency, but testing programs that use that concurrency is hard. We can write simple idiomatic code that's impossible to test quickly and reliably, or we can write testable code that's complicated and unidiomatic. So we asked ourselves, what can we do to make this better? One obvious feature is a better way of waiting for quiescence. We want a way to ask the runtime when background Go routines have finished their work. We want to be able to limit the scope of this query to a single test so that unrelated tests do not interfere with each other. We also want better support for programs that use fake time in tests. It isn't hard, as I said, to make a fake time implementation, but code which uses an implementation like this is not idiomatic. Idiomatic code will use a time.timer, but it's not possible to create a fake time.timer. So we asked ourselves, should we provide a way for tests to create fake time.timers where the test controls when the timer fires? A testing implementation of time needs to essentially define an entire new shadow interface covering the time package with real and fake implementations, and pass that to everything that operates on time. We asked ourselves, should we define a common interface like that and put it in the time package so that it could be implemented for tests? In the same way that net.con is a common interface describing a network connection. But what we realized is that unlike a network connection, there really is only one possible implementation of fake time. A fake network might want to introduce latency or errors, but time really does only one thing. It goes forward. Tests need to control the rate at which time progresses, but if a timer is scheduled to fire 10 seconds in the future, it should always fire 10, possibly fake, seconds into the future. And in addition, we don't want to upset the entire Go ecosystem. Most programs today are written to use functions in the time package. We want to keep those programs not just working, but idiomatic. It shouldn't be unidiomatic to call time.now, for example. So what this led to is the conclusion that what we need is a way for a program to tell the time package to use a fake clock in much the same way that the Go playground uses a fake clock. Unlike the playground, we need a way of limiting the scope of this change to a single test. And so, in Go 124, we introduced a new experimental package to simplify testing concurrent programs. The package is called testing/synctest, and it lets you run a test function in what we're calling a bubble. Within the bubble, the time package uses a fake clock, and the synctest package provides a function to wait for the bubble to quiesce. Over the last few months, we've gathered feedback from early adopters, and thank you very much to all of you out there who tried it out, especially those of you who reported back on your experiences. We made a number of changes to address problems and shortcomings, and I'm excited to say that the synctest package will be part of the standard library in Go 125. Okay, I'm done. So let's actually look at it. The synctest package contains two functions, just two. Test executes a function in a new bubble, and wait blocks until every goroutine in the bubble is blocked waiting for some other goroutine in the bubble. We call that state being durably blocked, when you can only be unblocked from within your same bubble. So let's look at an example of synctest in action. This might look a little familiar. This is the naive test for context.withDeadline that we looked at earlier. The only changes are that we've wrapped the test in a synctest.test call to execute it within a bubble, and we've added a synctest.wait call. This test is fast and reliable. It precisely tests the expected behavior of the system under test, and it also requires no modification to the context package. Using the synctest package, we can write simple idiomatic code and test it quickly and reliably. This is a very simple example, of course, completely trivial, but this is also a real test of real production code. If synctest had existed when the context package was written, we'd have had a much easier time writing tests for it. Time within the synctest bubble behaves much the same as fake time in the Go playground. The time starts at midnight, January 1st, 2000 UTC. If you need to run a test at some specific point in time for some reason, you can just sleep until then. It doesn't take 25 years to sleep for 25 years. Time only passes when every goroutine in the bubble has blocked. You can think of the bubble as simulating an infinitely fast computer where any amount of computation takes no time at all. So the first t.log in this example will always print that 0 seconds of fake time have elapsed since the start of the test, no matter how much real time has passed. The time.sleep call will return immediately rather than waiting for 10 real seconds, and the second t.log will print that 10 fake seconds have passed since the start of the test. The synctest.wait function lets us wait for background activity to complete. If we didn't have the wait call in this test, we would have a race condition. One goroutine modifies the done variable, while another reads from it without synchronization. The wait call provides that synchronization. Many of you are probably familiar with the -race flag, which enables the data race detector. The race detector is aware of the synchronization provided by wait and does not complain about this test. If we forgot the wait call, the race detector would correctly complain. Wait provides synchronization, but the passage of time does not. So in this example, one goroutine writes to a done variable while another sleeps for 1 nanosecond before reading it. And it should be obvious that if we run this with a real clock outside of a synctest bubble, this code contains a race condition. Inside a synctest bubble, the fake clock ensures that the sleep will not return until the writing goroutine has finished its work. However, the race detector will report a data race because one would exist were this code run with a real clock. When we add a wait call here, that provides explicit synchronization and fixes the data race. Taking advantage of the synchronization provided by wait can allow us to write simpler tests with less explicit synchronization. For example, let us consider this test of io.copy. io.copy copies data from a reader to a writer. You might not immediately think of this as being a concurrent function, since it blocks until the copy has completed. However, providing data to io.copy's reader is an asynchronous operation. Copy calls the reader's read method, read returns some data, and the data is then written to the writer at a later time. In this test, we're verifying that copy immediately writes any new data to the writer rather than waiting to fill an internal buffer before copying it. So we start by creating an io.pipe to serve as the source that copy reads from. io.pipe returns a reader and writer that are connected by a pipe. We then call copy in a new Go routine, copying from one end of the pipe into a byte-stop buffer, which is what we're going to examine at the end of our test. We then write to the other end of the pipe, the right end of the pipe, and wait for copy to handle the data. And finally, we verify that the destination buffer contains the desired data. We don't need to add a mutex or other synchronization around the destination buffer because the synctest.wait call has ensured that it is never accessed concurrently. This test demonstrates a few important points. Even synchronous functions like io.copy, which do not perform any additional background work after they return, may exhibit asynchronous behaviors. Using synctest.wait, we can test those behaviors. And note also that this test does not work with time in any way. Many asynchronous systems involve time, but not all of them. The synctest.test function waits for all the Go routines in the bubble to exit before it returns. Time stops advancing within the bubble after the root Go routine, that is, the Go routine started by test, has returned. So in our first example here, test waits for the background Go routine to run and exit. In the second example here, we schedule an afterfunc for a time in the future. The bubble's root Go routine returns before that time is reached, so the afterfunc simply never runs. And in the third example, we start a Go routine that sleeps. The root Go routine returns and time stops advancing, and the bubble is now deadlocked because test is waiting for all Go routines in the bubble to finish, but the sleeping Go routine is waiting for time to advance. The synctest package detects when a bubble is deadlocked due to every Go routine in the bubble being blocked on another Go routine in the bubble and panics. The runtime will print stack traces for every Go routine in the deadlocked bubble. When printing the status of a bubbled Go routine, the runtime indicates when the Go routine is durably blocked, that is, blocked waiting for another Go routine in the bubble. You can see that the sleeping Go routine in this test is durably blocked. Durably blocking is a core concept in synctest, possibly the core concept. A Go routine is durably blocked when it is not only blocked, but when it can only be unblocked by another Go routine in the same bubble. When every Go routine in a bubble is durably blocked, then synctest.wait returns if it has been called. If there is no wait call in progress, then fake time advances instantly to the next point that will wake a Go routine. And if there is no such time, the bubble is deadlocked and the test fails. It's important for us to make a distinction between a Go routine which is merely blocked and one which is durably blocked. We don't want to declare a deadlock when a Go routine is temporarily blocked on some event arising outside of its bubble. So let's look at some ways in which a Go routine can block non-durably. The most important limitation is that I/O is not durably blocking, notably including network I/O. A Go routine reading from a network connection may be blocked, but it will be unblocked by data arriving on that connection. This is obviously true for some connection to a remote network service, but it's also true for a loopback connection, even when the reader and writer are both in the same bubble. When we write data to a network socket, even a loopback socket, the data is passed to the kernel for delivery. There's a period of time between the write system call returning and the kernel notifying the other side of the connection that data is available. The Go runtime cannot distinguish between a Go routine blocked waiting for data that is already in the kernel's buffers and one blocked waiting for data that simply will not arrive. This means that tests of networked programs using synctest usually cannot use real network connections. Instead, they should use an in-memory fake. I'm not going to go over the process of creating a fake network here, but the synctest package documentation does include a complete worked example of testing an HTTP client and server communicating over a fake network. syscalls and cgo calls are not durably blocking because we can only reason about the state of Go routines executing Go code. Perhaps surprisingly, mutexes are not durably blocking, and this is a decision born of practicality. Mutexes are often used to guard global state, so a bubbled goroutine will often need to acquire a mutex held outside of its bubble. But mutexes are also highly performance sensitive, so adding any additional instrumentation to them risks slowing down non-test programs. So synctest can test programs which use mutexes, but the fake clock will not advance while a goroutine is blocked in mutex acquisition. This hasn't actually posed any problems in any cases we've encountered, but it is something to be aware of. So what is durably blocking? Time.sleep is obviously durable. Time can only advance when every goroutine in the bubble is durably blocked. Channel operations on channels created within the same bubble are durable. We make a distinction between bubbled channels created in a bubble and unbubbled channels created outside any bubble. This means that a function using a global channel for synchronization, for example to control access to a globally cached resource, can be safely called from within a bubble. Trying to operate on a bubbled channel from outside of its bubble is an error. We also associate weight groups with bubbles. Weight group doesn't have a constructor, so we do the association implicitly on the first call to go or add. And as with channels, waiting on a weight group belonging to the same bubble is durably blocking, and waiting on one outside is not. Calling add on a weight group belonging to a different bubble is an error. Waiting on a sync.cond is always durably blocking. Waking up a goroutine, waiting on a cond in a different bubble is an error. And finally, an empty select is durably blocking. And that's the complete list of durably blocking operations. It isn't very long, but it's enough to handle almost all real-world programs. The rule is that a goroutine is durably blocked when it is blocked, and we can guarantee that it can only be unblocked by another goroutine within the same bubble. And in cases where it's possible to try to wake up a goroutine from outside of its bubble, we panic, usually fatally. For example, it's an error to operate on a bubbled channel from outside of its bubble. I'm pretty happy with the synctest package at the moment. Aside from the inevitable bug fixes, I don't expect any major changes to it in the future. Of course, with wider adoption, it's always possible that we'll discover something that needs doing. One possible area of work is to improve the detection of durably blocked goroutines. It'd be really nice if we could make mutex operations durably blocking, probably with a restriction that a mutex acquired in a bubble must be released within the same bubble. Testing networked code with synctest requires using a fake network. The existing net.pipe function can create a fake net.con, but there's currently no standard library function that creates a fake listener or packet con. And in addition, the con created by net.pipe is synchronous. Every write blocks until a read consumes the data, which is not really representative of real network behavior. So perhaps we should add a really good fake implementation of common network interfaces to the standard library. So that's the synctest package. I can't say that it makes testing concurrent code simple, because concurrency is never simple. But what it does do is let you write the simplest possible concurrent code using idiomatic Go and the standard time package, and then write fast, reliable tests for it. I hope you find it useful. Thank you. And the timer says I have 1 minute and 30 seconds left. So after my acknowledgments, I'm going to give you one bonus slide, if you don't mind.
Okay.
So first, thank you to Brad Fitzpatrick for suggesting, hey, what if we just parse those stacks? Russ Cox for messaging me at one point and saying, I think that you're assuming that the runtime is never going to help you here, but what if it did? Michael Pratt for his really wonderful code reviews of all of this. Thank you for volunteering for that. Everyone who gave feedback on this and the entire Go team, you people are wonderful, and I can't believe you let me do this crazy thing. So in 124, we released this package as an experiment. You had to set go experiment equals synctest to turn it on. And based on the feedback we got, we made a bunch of changes to this package. So here's a quick rundown of changes that we made. We started out with a run function that just executes a func. And we changed that to a test function that takes a testing.t and then calls a function with a new testing.t. And that's because we realized that you really want to have a t that's scoped to the lifetime of a bubble, so that if you call a cleanup function, it runs in the bubble as opposed to outside of it. We also made it so that time stops when the root go-routine returns. Previously, when the root go-routine returned, if there was anything still sleeping, we'd just keep on waiting or advancing time. And that gets really confusing if you have something which is reading from a time.ticker, because it just runs forever, and your test never returns, and you don't know why that is. We fixed a bunch of cases where durable wasn't actually durable, and I have 2 seconds left, so that's it. Thank you very much.